Welcome to CS 1401 Video 18.2. In the previous video, I compared iterative versus recursive algorithms for linear search and for computing numbers in the Fibonacci sequence. In this video, I'll compare iterative versus recursive algorithms for binary search. I want to tackle the following problem. Given a sorted list, determine if a particular element is in the list. Of course, this assumes that the elements can be sorted. To keep matters simple, I'll work with integers. But in general, the list elements could be anything that can be sorted, like people, sorted by height, for instance. Here's an example of such a problem. Determine if 7 is in the list 1, 2, 4, 6, 8, 9. We could apply our solution to the linear search problem to this problem. But I say that we can do better than that. For instance, why range over all the elements if we can at once discard half of the elements? How can we do that, you ask? Think of it. When you are asked to guess a number between 1 and 100, do you go 1, 2, 3, 4, 5, etc.? No! You go for 50 and ask if the number to be guessed is lower or higher. Based on the answer, you can now discard half of the possible numbers. Once this is done, you repeat the process until you guess the number. In the case of our binary search, you repeat the process until you find the number or you conclude that the number is not present in the list. Now, let's put our approach together in somewhat rough pseudocode. Our algorithm will be called binary search and will take an array of integers and as a second parameter, the desired element. We'll look at the middle element of the list. If the desired element is equal to the middle element of the list, I'll return true. Hey, we found that the element is in the list. Else, if the desired element is less than the middle element of the list, I'll look for the desired element in the first half of the list. Else, I'll look for the desired element in the second half of the list. And if I don't find it, I'll return false. Note that this pseudocode involves a repeated process. We keep looking for the desired element if we have not found it yet. This can be modeled and implemented as iteration or as recursion. Let's start with recursion. I can see in the pseudocode that the algorithm keeps calling similar functions. Look for desired element in the first half of the list, or look for desired element in the second half of the list. Such a call requires the following parameters: the list in which we are looking, the desired element, and the bounds of the search. For example, if we are looking in the first half, the bounds would be 0 to middle index minus 1. And if we are looking in the second half, the bounds would be middle plus 1 to length minus 1. Why don't we look at middle? Because that's the element we've already just checked. This means that we are augmenting the original parameters of binary search, which were int array of list and int desired element, with two new parameters representing the boundaries of the search, int start and int end. So now we know that the full signature for binary search should be binary search of an array of integers called list, an integer that's the desired element, an integer representing the index in the array where we're going to start our search, and an index representing the point in the array where we're going to end our search. As a result, when we first call this functionality, for example, looking for 7 in list 1, 3, 5, 6, 7, 9, 11, 14, 20, which has 9 elements numbered from 0 to 8, we actually call binary search of that array, 7, which is the desired element, 0, which is our start index, and 8, which is our end index. With that insight, I can now write a program in Java for binary search that takes the recursive approach. The method is called binary search and it returns the Boolean value true or false. It takes the array of integers, the desired element, our start index, and end index. If start is greater than end, well, that means we've looked at every element in the part of the array that we're examining, in which case the desired element isn't there, so we'll return false. If the desired element is equal to list of start plus end over 2, that's the middle element, well, then we return true because we found it. Else, if the desired element is greater than the value of the middle element, then it's going to be in the upper part of the list, so we'll return the result of searching the list for the same desired element, starting at middle plus 1 and ending at the end index. Else, and in this case, this means that the desired element is less than the middle element, we'll return the result of doing binary search on the list with the same goal, starting at the start and ending at the middle minus 1. Just like with the Fibonacci numbers, the recursive implementation follows elegantly the idea we had about how to solve this problem. The finished code is almost the same as the rough pseudocode. And in this case, the recursive algorithm is efficient, so we don't have to worry about our computation taking zillions of times longer than the iterative version. Let's look at the iterative version anyway. In the iterative version, since we do not know in advance how many times we are going to have to run the process of looking in half of the current area of interest, we can't use a for loop, which means we will have to use a while loop. This forces us to define a condition under which the while loop is allowed to be executed, and, most important, when it should stop. Actually, the implementation doesn't really change anything about the underlying algorithm, which is about looking for the desired element in a given part of the array. The search should stop when this part is non-existent, which is when the start and end cross, which we can evaluate as start greater than end. Let's look at the iterative solution now. The method binary search returns a Boolean value of true or false. It takes the array of integers called list and the desired element as arguments. We'll start at the start index of the array, and the end will be list.length. While start is less than end, if the desired element is equal to the middle element, then we'll return true. Else, if the desired element is in the upper part of the list, that is, it's greater than the middle element of the list, we'll set start to the middle element plus 1, and end will stay the same, which is the current end. Otherwise, if the desired element is in the bottom half of the list, then we'll set end equal to middle minus 1, and of course the start will stay the same. Finally, if we haven't found the element by the time the start and end cross, then we return false. Okay, so the iterative implementation is not as similar to our original pseudocode as was the recursive version, but it's not that bad. When efficiency is not an issue, the choice of implementation mostly depends on your own choice of style. At the start of this course, I noted that computer science is about doing things with information in ways that are correct, efficient, usable, secure, and economical. In later courses, you'll learn about how to determine correctness, how to assess usability and security, and how to build systems economically. But you already have a start on understanding the impact of efficiency. In videos 18.1 and 18.2, we've looked at iteration versus recursion for 3 different kinds of computing problems. The answer to the question of iteration versus recursion often comes down to your own problem-solving style. But in some cases, though, the efficiency factor completely determines which approach you should use. This is the case of Fibonacci in particular. Solving this problem with recursion is extremely inefficient, and solving it with simple iteration proves to be much more efficient. You will hear and learn later in your curriculum about what is called dynamic programming, which is a problem-solving approach that enables you to follow a recursive thinking process while avoiding the risk of redundant computations. In the next set of videos, we'll leave Java for a while to explore implementation of algorithms in the logic programming language Prolog. See you then.